No, they're not here yet. So let me just let everybody join. So
yes.
Okay. So welcome everybody. I'm just a few seconds to let everybody join. Okay. All right. So welcome. Cuimin, do you mind putting your slides up now, please? So welcome everybody. Today we have a special version of VSET because we have Cuimin Ba. She's from the University of Pennsylvania, and Cuimin won the paper for the award for best paper at the recent Women in Economic Theory student conference that took place in October. We also have a conference organizer, Sulanya Dasgupta and Elena Istumina here with us. We also have two very important panelists, Drew Fudenberg and Boton Kosegi, who are joining us and will be following Cuimin's presentation. I always want to mention Kate Wang from Caltech, who won honorable mention for learning repeated interactions in networks. Now, Cuimin's paper,
it's basically gone. It's like really annoying. It's like.
Drew, do you mind unmuting yourself? Now, and Cuimin's paper is titled Robust Misspecified Models and Paradigm Shifts. Just a reminder, next week we have Jacob Leshno from Chicago booth, and he'll talk about price discovery in waiting lists. So Cuimin, the floor is yours. You can start.
Thank you. Thank you so much for having me here today. I am really grateful for the chance to share my JAMA paper, both at the Women in Economic Theory conference and here today at VSET. So let me just get started. Okay, so in this complicated world, individuals often rely on models to guide their decision-making process, whether it be financial models, demand and supply models, and even political stories. Now, models, because they are subjective, they're often misspecified due to cognitive constraints and psychological biases. So for example, it has been widely documented that people exhibit many forms of biases, such as oversimplification, under or overreaction to new signals, overconfidence in one's ability, or correlation neglect, and so on and so forth. Now, there's been a growing literature in recent years that explores the consequences of model misspecification, and they focus on the analysis of a dogmatic agent who commits to a misspecified model and never considers changing this model. Now, from this literature, we know that using misspecified models can cause suboptimal decisions in the long term. However, taking a step back, if people are using a wrong model and they are aware of potential model misspecification, then we might expect them to switch to a better alternative as they collect data over time. And so my questions are, can a misspecified model persist in the long term if people entertain competing models and can switch to a competing model? And if the answer is yes, then which models are more likely to persist than others? And how do environmental factors would contribute to their persistence? So to address those questions, I developed a new learning framework that allows for sticky model switching. So there are many examples of people switching models when they find a competing model more compelling. For example, Thomas Kuhn proposed the famous concept of paradigm shift to characterize scientific revolutions. And the classical example of this is the paradigm shift from a Ptolemaic cosmology that puts the Earth in the center of the universe to a Copernican cosmology that puts the sun in the center of the universe. Now, in the Ptolemaic paradigm, the Mars moves in the weird retrograde orbit. However, in the Copernican paradigm, everything moves in a circular uniform motion. And so evidently from this picture, the new paradigm fits better than the old paradigm and gradually replaces this. Okay, so following this spirit, in my framework, I have an agent who subscribes to one model and uses one model to make decisions at any point of time, but can switch to a competing model if that model fits the data sufficiently better. Okay, so what's happening here is that my agent, instead of assigning beliefs to different models and averaging their predictions, my agent subscribes to one model and switches it across models in a but non-Bayesian way. So here you might ask, why is this a good model of human behavior? So I would argue that in addition to a large amount of empirical evidence for this type of switching behavior, I would say that it is simply implausible to imagine an agent could attach well-articulated probabilities to every possible model of this world. So, for example, a central bank cannot develop a policy using every model that economists have ever developed, not to mention these models, not to mention those models economists have not yet developed. And people rarely entertain multiple models at the same time, especially when they contain conflicting ideas, such as the Ptolemaic paradigm and the Copernican paradigm. So given that people don't entertain all possibilities of the world, there are occasions where they need to change their mindset, and this cannot be captured by a Bayes rule. So what this paper is doing is to take a natural, non-Bayesian approach and study its implications on model persistence. Okay, given this framework, I am interested in which model persists, in the sense that with positive probability, it is eventually adopted forever. And I'm also interested in which model is robust, in the sense that it persists against a wide range of competing models. Okay, now before I tell you about my results, I want to use a stylized example to describe the sort of active learning framework setting that I want to capture, and to illustrate the main forces at play that make a model persistent or not persistent. And here I'll build my example on the great paper by Heithaus, Kozegi, and Strack. One of them is our panelist today. And in this example, I'll be talking about over and under confidence. Okay. So imagine that our agent is an artist who chooses how much costly effort to exert every day. So he chooses 80 from 0, 1, and 2, and incurs the cost of effort that's increasing and convex in his effort. Now, our artist makes money from selling paintings. And so by the way, this Picasso painting appears on our poster for this presentation today, and I thought it's brilliant, so I put it here. So our artist maximizes the sales of his paintings minus the cost of effort. And the sales of his paintings takes this really simple form. It depends not only on his effort, AP, but also his talent and the market demand for art and some random noise. And let's assume that his true talent is 1 and the true market demand is 2. Okay, now suppose that our artist just graduated from art school, and so he's uncertain about the market demand. He has a non-degenerate prior about the market demand and updates his belief by actively exerting effort and observing the sales. Okay, however, the artist is endowed with a misspecified model in that he has a biased self-perception and assigns probability 1 to a talent hat that deviates from its true value of 1. So of course, this is a stylized and simplifying assumption here, but I want to, so through modeling the artist treating the market demand and his talent in different ways, I want to capture this idea that individuals often commit fundamental attribution errors, and they are slower in changing their self-perception than in updating beliefs about the outside environment. Okay, so let's first imagine that our artist mistakenly thinks that he has no talent at all because, for example, his master at art school was very critical of his work. And I captured this self-view by assuming the artist believes that his talent is given by this talent hat that equals 0, lower than its true level. And suppose for some reason, our artist starts to entertain a competing model with the correct belief about talent. Then is underconfidence and this misspecified model that it gives rise to going to persist? The answer is no. In this case, underconfidence is unlikely to persist. And let me show you why. So I'm going to do a steady state analysis here. Let's assume that the agent exerts an effort of 1. Then his correct competing model is going to predict the correct amount of cells, since it's correct. So this correct cells is going to be generated by an effort of 1, a true talent of 1, a true market demand of 2, which amounts to 4. So to make sense of this data, the artist's underconfident model has to induce the artist to believe that the market demand is instead given by 4. Okay, but given this high belief in market demand, our artist would then find the high effort of 2 to be optimal.
Cuimin, are you going to tell us why the artist starts off exerting an effort of 1? You said just assume that, and I mean, you haven't told us what the artist is maximizing or anything, or what their beliefs are. So it's hard to evaluate this one slide without a bit more of the model.
Okay, so the artist maximizes the, let's go back to this. The artist maximizes the cells minus the cost of his effort. And what I'm doing here is to invite you to imagine a steady state, or what would happen in the long term, by saying that if the artist exerts this effort, then he would arrive at this effort, and then he maximizes he does this maximization problem, and then his belief is going to lead to an optimal effort. Does that make sense? So let's keep going, and I hope this would become clear. Okay, so given this high belief in market demand, then our artist would find the higher effort of 2 to be optimal. However, when he starts to play this effort of 2, then the true competing model continues to predict the true amount of cells, which in this case has increased to 6. Okay, but to make sense of this data, our artist has to believe that the market demand is given by 3 instead. But given this lower belief, our artist would find the lower effort of 1 to be optimal, and he would go back to the place he starts with. Okay, so what I'm describing here is that the artist would, in the long term, oscillate between an effort of 1 and 2. And what happens is that no effort choice is a self-confirming equilibrium, because there is no effort choice that is both, and there is no effort choice such that there exists this demand hat that both explain the data the artist is observing and supports this effort choice. And so in the long term, the true competing model is always going to fit consistently better than the misspecified underconfidence model. And so the underconfidence model does not persist, and the artist would switch to the competing model sooner or later. Okay.
Joe, do you want to make that point explicitly? Unless
let's wait for the model. That was to the audience. That's fun.
So what I'm describing here, this is a heuristic way of describing the dynamics of actions and beliefs. And I can now, if we want to be more serious, then my prediction is that in the long term, the artist would oscillate between effort 1 and 2 forever. Okay. Now, next, let's consider the other case of an overconfident agent. Let's suppose that the artist is overconfident because his master at art school told him to have faith in himself. And so he believes that his talent is given by 2 instead. And again, this gives rise to a misspecified model, because the true relationship between the effort and cells is not included in this model. And suppose again, the artist entertains a correct competing model. The question is overconfidence going to persist? Then, in contrast to the underconfidence case, this time the answer is yes. And let me explain why. So again, I will do a steady state analysis. So suppose that the artist exerts an effort of 0. We're going to explore whether this effort choice is stable in some sense. So given this effort choice, the true competing model continues to predict the true amount of cells, in this case is given by 2. And it turns out that the overconfident model can explain this data equally well by inducing the artist to believe in the market demand of 1, lower than its true value. So the artists attribute the lower than expected sales to a low market demand. Now, importantly, given this low belief in market demand, our artists would indeed find zero effort optimal. So what it means is that zero effort is a self-confirming equilibrium. And given when this artist is playing this equilibrium, it seems that his misspecified initial model would predict as well as the correct competing model. And so it seems that the artist has no reason to switch. But this is not the whole story yet. Even if there exists such a self-confirming equilibrium, we cannot say for sure that the model persists, because the steady state analysis doesn't tell us whether the agent would stick to his model as he learns and converges to the steady state. And this is related to the point that Drew mentions. So in fact, later, my characterization results would show that we also need the artist to start with a relatively entrenched prior around the self-confirming equilibrium, so that he does not switch to the competing model before he can get stuck with the equilibrium. Okay.
So I have a question. Just feel free to put it off, but so it seems like the key thing is whether there is a self-confirming equilibrium, and that doesn't seem closely related to overconfidence versus underconfidence. Is there a general argument that there's more likely to be a self-confirming equilibrium with underconfidence? Oh, sorry, with overconfidence?
So yes, exactly. So the true reason for why there is this dichotomy between over and underconfidence is that overconfidence leads to positive belief reinforcement and the convergence to a steady state that's a self-confirming equilibrium, whereas underconfidence leads to negative belief reinforcement and oscillation between non-confirming actions. So exactly, this their difference stems from the different directions in the belief reinforcement. And why do they have this different directions in belief reinforcement? So let's go back to this and just notice that effort and the market demand are complements. And so this means that when the agent exerts a higher level of effort, the marginal return to the market demand actually increases. And so the artist does not have to distort his belief about the market demand that much to explain any discrepancy between his expected sales and the true sales. And so a higher effort level would tend to correct his belief distortion. However, the difference between over and underconfidence is that overconfidence leads to an underestimation of the market demand and a low effort. So in that case, belief distortion is self-reinforcing, whereas in underconfidence case, that leads to an overestimation of the market demand and a high level of effort. And so that leads to a self-correcting, that leads to a belief distortion that's self-correcting. And therefore the belief reinforcement is negative. And this, of course, this insight could be generalized to in the paper, I consider this application to generalize this insight to allow for more general payoff functions and outcome distributions. Okay, so
I see this reinforcement. What I don't see is why with negative you necessarily get cycling, and with positive you get convergence.
Okay.
Yeah. But
Great.
maybe it's not the right time.
We can talk about this later, but yes, there is a caveat for the logical link between negative reinforcement to there exists no self-confirming equilibrium. So what happens is that for intermediate level of underconfidence, the effort level is super sensitive to the beliefs, and then negative belief reinforcement would imply that there exists no self-confirming equilibrium. However, for more extreme levels of underconfidence, the effort level is less sensitive, and there would exist a self-confirming equilibrium. But we can talk about this later. Okay, now the second lesson we learned from this example is that a simple steady state or simple self-confirming equilibrium analysis is not sufficient to predict persistence, nor does it help to clarify the role of environmental factors. So we need a full-fledged model switching framework to characterize model persistence and to understand the role of the other factors, such as within model priors, the evidence threshold that would trigger a switch, and which competing model is entertained. And all those factors would matter for the model switching dynamics. Okay, then next, I am going to describe my model switching framework and then talk about my results. I have an infinite horizon decision problem. In each period, my agent chooses an action from a finite action set A, such as choosing an effort, and then observes a random outcome YT from a set Y, such as observing the amount of cells. And then our agent obtains a flow payoff U that's jointly determined by both the action and the random outcome. For example, in the motivating example, the flow payoffs is the amount of cells minus the cost of effort. Okay, now the true data generating process, or true DGP, is the true mapping between actions and the distribution of outcomes. It is fixed and unknown. And it prescribes that the random outcome YT is drawn from distribution density Q star. So in the motivating example, the amount of cells would depend on the artist's effort. Now, if the true data generating process is known by the agent, then she will just figure out the optimal action and play that every single period. But given that the true data generating process is unknown, our agent has to learn using subjective models. Also forgot to mention that for the main analysis, I'm going to assume my agent is myopic. However, if I have time at the end of this presentation, I can talk about how to relax this assumption in a way such that I can preserve most of my results. Okay, great. Then what exactly is a model? A model is a parametric theory of how actions would affect the outcome distribution. And it would consist of two things: a finite parameter space, capital omega theta, and a set of predictions. So for each parameter value, little omega, in the parameter set, the model predicts a data generating process, Q theta, that maps actions to outcome distributions. But what are parameters? Parameters can capture any uncertainty within a model that needs to be resolved via learning. So, for example, this could be uncertainty about the state of the world. In the artist's overconfidence model, the parameter is just the market demand, which is to be estimated from data. But in a linear supply model, the parameters could just be the slope and the intercept of the linear supply function. I use capital theta to denote the universe of all models that satisfy the standard absolute continuity assumption. So this means that there are no possible outcomes that would be ruled out by any of the subjective models. And I would say model theta is correctly specified if we can fine-tune this model to match the truth. Or more formally, this means if there exists a parameter value such that the prediction would correspond to the true data generating process for all actions. And misspecified otherwise if there doesn't exist such a parameter.
Cuimin, can I ask, is this,
Sure.
Are you assuming that there is a unique model that has a unique parameter, or could different models for different parameters equally generate the Q star?
Thank you for the question. So different models, they can have different parameter spaces and different predictions. And none of them has to be the correct specified model. But there is one model that I would call the the true model. So if I say true model, that would mean that would be referring to a model with a single parameter and that corresponds to the true data generating process.
Okay, just to clarify, you are assuming there is a unique theta that for which there is a unique omega such that this identity at the bottom is satisfied. You do not allow for two different thetas to have two different omegas that would satisfy this identity.
So omegas are just labels. What really matters here is the data generating process. So it's the Q of theta conditional on omega. So we can have like two different models. They have different parameter spaces, and they could, like, the parameters can have totally different connotations, but their predictions are actually the same thing. Does that make sense?
So you are allowing. Okay.
Yes, exactly. Thank you for the question. Okay, so the literature often studies what I call a dogmatic modeler who has only one model, but I focus on a switcher who can switch between multiple models. I would call a dogmatic modeler who commits to model theta a theta modeler. Now, I would focus on this switcher who has at least two models, but for the main analysis, I'm going to focus on two models only. So the switcher has one initial model theta and one competing model theta prime. And as illustrated in this graph, as mentioned by Francesco, the two models, theta and theta prime, they can have very different predictions, Q theta and Q theta prime. They can have very different parameter spaces, omega theta and omega theta prime. None of them has to be correctly specified, in the sense that they contain a parameter value that would correspond to the true data generating process. Okay, so this is a really general learning framework. Now, my agent learns within each model about the parameters in a Bayesian way, but she can also switch between different models in a non-Bayesian way that I'm going to talk about soon. First, let's see how the agent operates within a model. Now, since she has two models, she has two full support priors, one for each model. So pi 0 theta is the agent's prior over theta's parameters. Pi 0 theta prime is her prior over theta prime's parameters. And if she adopts theta in period t, then our agent would update her belief to pi t theta by a Bayes rule using all past history of outcomes and actions. And then she would take an optimal action as predicted by her current model theta, given her posterior. Now, she will be doing similar things if she adopts theta prime in this period, but the parameters she'll be updating on and the action rule she would adopt would be specific to model theta prime. Okay, so next let's talk about how the agent switches her model. Let this empty denote the model choice in period t. And so M0 is just the initial model of theta. The model choice is in subsequent periods, MT, will be chosen by a Bayes factor rule. So what I mean, let this alpha be a constant larger than 1, and we'll call it the switching threshold. Our agent would calculate the Bayes factor or the data's likelihood ratio under model theta relative to the likelihood of under model theta prime relative to under model theta. And I'll introduce this object in more detail on the next slide, but roughly speaking, this measures how well theta prime fits the data compared to model theta as of period t. So using this graph here to illustrate how this works, the agent starts out by adopting model theta. If the Bayes factor is strictly larger than the switching threshold, then she would switch to the competing model theta prime. But in the future, if the Bayes factor is ever strictly lower than 1 over alpha, then she would switch back to model theta. So you will probably notice that I am assuming symmetry in the amount of evidence you need to switch in either direction, but this symmetry is actually not essential for my results. Okay. So an important concept here is the switching threshold alpha. When this alpha is larger than 1, we have switching stickiness. And the higher the switching threshold becomes, the more stickiness we have in switching. I'll be interested in the comparative statics with respect to the switching threshold. So let's look at this.
Can I ask, I'm very sympathetic, super sympathetic actually, and I don't have better ideas, but something bothers me, which is you were saying that people cannot keep two models in their heads at the same time and deal with them in a Bayesian way. That was kind of one of the motivations, right? But here, what they're basically updating in both models, and they're calculating the likelihood ratio. That's awfully close to what they need to do to also do Bayesian updating between the two models. But they don't do that. Like, how do you think about that? Like, what's going on?
Okay. Wonderful. So I think my motivation is not that the agent cannot entertain two models at the same time. So if the agent entertains two models at the same time, that becomes a hybrid model, and that becomes the initial model of the agent. What I'm saying is that the agent cannot entertain all models of the world at the same time. So that means that the agent's initial model has to be imperfect in some sense. And so there are important occasions where the agent needs to change that model. And that will be the occasion where the Bayes rule cannot capture, because for the Bayes rule to work, you need to assign positive probability to each model. But here I'm talking about a process. It's from a Bayesian weight from 0 to a positive number in some sense. Okay, great. So let's look at this Bayes factor more closely. If we expand it, then it would be as follows. So the likelihood of a model is given by the likelihood of the history of outcomes from y0 to yt-1, conditional on the past action history and a given parameter value, summed up across all parameter values, and the weight is taken to be the prior, y0. Okay, so here the Bayes factor is written in terms of the parameters are weighted using the prior. But we can also write this Bayes factor in a recursive form in terms of the posterior. So the Bayes factor lambda t can be decomposed into lambda t minus 1, the Bayes factor in the last period, and the likelihood ratio for the most recent outcome, yt minus 1. And here the parameters are weighted by the posterior.
Cuimin, this is a sensible model and it's clear, but I wanted to ask you about an alternative. But here, the agent summing over all possible parameters, and a alternative that comes to mind is for each model class theta, look for the parameter that best fits the data you have. I mean, if one parameter really fits your data well, the others don't, why should you penalize the model because it happened to include a bunch of parameters that didn't fit? I mean, which is what you're doing here.
Okay, that's a wonderful question. So I am using the prior to weight the parameters instead of the posterior to weight the parameters for all past outcomes, or I am also not using the maximum likelihood estimates to replace this parameter right here. So the main reason for that is that I want to penalize complex models. So to see this point, let's imagine a thought experiment where we just expand the parameter set of a model. Then with a larger parameter set, since we're including more data generating processes, the maximum likelihood across all parameters is guaranteed to be weakly higher. But that is not good, because that would imply that a bigger model is always better. Whereas in reality, we often see people have clear preference for simpler models. And the great thing about Bayes factor is that it automatically imposes a penalty on complexity. As the parameter set expands, the prior tends to be more diffuse because there are more parameters. And so this would thin out the weighted sum of the likelihood. Okay, so this is the reason why the Bayes factor would penalize complexity. And in fact, this would be important for one of my results that I'm going to talk about later. Fantastic. So that's our model switching framework. And now I'm going to talk about important concepts and their characterization. Okay.
Here, I think you're really using the assumption there's only a finite number of parameter values in a model, as opposed to a finite dimensional model class where the parameters could take real values. I mean, so that's okay. I mean that rules out the case where, like, the agent thinks is predicting coin flips and thinks all P's are possible. The agent is going to be forced to have a finite grid of possible P's.
Yes, you're exactly right. So here in this paper, I am restricting attention to finite parameter sets. So extending this framework to continuous parameter set, that would be possible, but is currently not in this paper.
Fair enough. Thank you.
Thank you. So next, I will talk about the important concepts. With these two models, there are three possible scenarios. Either the model choice eventually equals the initial model theta, or it oscillates forever between the two models, or it eventually equals the competing model theta prime. I am going to focus on the first scenario and name it persistence. So formally speaking, a model theta persists against theta prime at this given priors if under those priors, the model choice eventually equals theta with positive probability. So with positive probability, there exists a finite time capital T such that from then on, the agent only uses model theta. Now, importantly, you will notice from this definition that persistence is prior sensitive, and it is relative to the competing model. Okay, so what this means is that suppose the competing model is a great model, then we might expect fewer models to persist against that. If the competing model is really bad itself, then we might expect more models to persist against that. And in most scenarios, like this choice of the competing model could be context dependent and cannot be predicted by the analyst. So from now on, I am going to take a robustness approach and consider which models persist against a wide range of competing models. So in the paper, I consider three different notions of robustness. Starting from the strongest one, global robustness requires persistence against any arbitrary competing model, including both fundamentally different new paradigms and local perturbations of the original model. Local robustness then limits the step size of switching and only requires persistence against the local perturbations of the original model. Constrained local robustness further limits the direction of switching and only requires persistence against local perturbations that are restricted to certain parametric families. So for example, if I start out with a linear model, I might want to preserve linearity in any of the competing model I am considering. Now today, because of the time constraint, I am going to focus on the first two robustness notions. Here is a formal definition for them. I say that a model theta is globally robust given this prior if it persists against every possible competing model in a universe of all models.
So
at every
question,
prior.
Has this universe capital theta been defined yet?
Yes, I have defined on the slide when I introduced the models. So it's the
okay.
Yes. So basically, it's the set of all models that satisfy an absolute continuity assumption. And so it would be the universe of all finite collections of data generating processes, if that makes it clear.
That makes it clear. Thank you.
Thank you. And further, a model is locally robust if there exists a positive epsilon such that model theta persists against every epsilon closed model at every epsilon closed prior. Now, what does it mean? So to make sense of this definition, of course, we need to formalize distance measures between models and their priors. So since a model is just a collection of data generating processes, I measure the distance between them by the standard Hausdorff distance between their corresponding sets of data generating processes. And I measure the distance between their priors by the Prokhorov metric over distributions over data generating processes. Okay, so now we have laid our foundation for our results. Next, I'm going to present the theorems. Theorem 1 characterizes which models can be locally or globally robust for at least one prior. Theorem 2 explores the dependence on the prior and asks at which priors are these models really locally or globally robust. As a first step, let's similar to what we do in the motivating example, it would be useful to consider this special case where the competing model is correctly specified. Then which models can persist against that? Such a true correct competing model can always match the data perfectly in the long term. So for a model to persist against it, it must also have perfect asymptotic accuracy. Otherwise, it would be replaced by the correct competing model sooner or later, right? So this tells us that such a model must induce the agent to play a self-confirming equilibrium in the limit. And here, this statement, it really has two different parts. So first, there needs to exist a self-confirming equilibrium. And second, that equilibrium has to be reachable and stable so that the agent can play it forever. I'm going to define these two parts separately. For the equilibrium concept, following the definition in Friedenberg and Levin, I say that the strategy sigma is a self-confirming equilibrium under model theta if there exists some belief pi theta over the parameters, and such that the strategy sigma is myopically optimal against this belief, and this belief is consistent at strategy sigma in the sense that for every action that's in the support of sigma, every parameter in the support of this belief is going to predict the correct outcome distribution. So this is why it's self-confirming. But just notice that the existence of a self-confirming equilibrium doesn't mean model theta is correct or that it induces the efficient action, because here I'm only requiring consistency for the equilibrium, for the actions that can be played in the equilibrium. So the model could be predicting really badly for off-task actions, for example. And next, let's turn to the stability condition. So I say that strategy sigma is P absorbing under model theta if under some full support prior, a theta modeler eventually only plays action in the support of sigma with positive probability. So here, P as in P absorbing means that this is a positive probability event. And the great thing about this stability notion is that it only concerns the problem of a theta modeler. And so I can characterize P absorbingness based on the primitives of model theta only. And let me mention that not all self-confirming equilibria are P absorbing. And so this stability condition is not vacuous. This lemma confirms our intuition that if theta persists against a correctly specified model, then it must admit a P-absorbing self-confirming equilibrium. Now, to reflect on this lemma, what this is saying, it is providing a necessary condition for global robustness, because that requires persistence against arbitrary competing models. But it is not clear yet whether that will be sufficient for global robustness, nor does it help to understand local robustness, because for local robustness, we are only requiring persistence against local perturbations. And for a misspecified model, a correct model may not be in the close proximity. But perhaps surprisingly, theorem 1 establishes that all the following are equivalent. So model theta is locally robust for at least one full support prior, if and only if model theta is globally robust for at least one full support prior. And both of them amount to the requirement that there exists a P-absorbing self-confirming equilibrium under model theta. Okay, so first of all, this result shows that while we might think that local robustness is much weaker, both of them require high asymptotic accuracy as captured by the existence of a P-absorbing self-confirming equilibrium. And so in this regard, taking small steps is as powerful as taking large steps. And importantly, this result also shows that misspecified models can be robust against arbitrary competing models, including the true model. So this is a formal learning foundation for certain types of misspecified models. And while this p-absorbingness may sound a little abstract, it can actually be characterized by really simple conditions. So this lemma is saying that a self-confirming equilibrium is p-absorbing as long as it is quasi-strict. And this is something that could be verified easily from the primitives. I want to use some time to give you some proof idea for this result. So first, let me explain why local robustness implies the existence of a p-absorbing self-confirming equilibrium. Say that we have a model, theta, that is misspecified. Now, the true data generating process could be distant from our initial model, so we cannot take the true model as the competing model. But what we can do is to perturb our model theta towards the true data generating process. So to do that, just notice that our model is a collection of data generating processes. So we can take a convex combination between every data generating process in model theta with the true data generating process. And because the Kullback-Leibler divergence is convex, this convex combination is going to weakly increase the prediction accuracy. And so this local perturbation would outperform our initial model unless the model itself cannot be improved, meaning that it already persists against the true data generating process. So by the lemma, this means that theta must admit a p-absorbing self-confirming equilibrium. This is the easy part for this theorem. Next, let's see why a p-absorbing self-confirming equilibrium implies global robustness for at least one full support prior. Now, this can feel very intuitive at first glance. The p-absorbingness implies that the self-confirming equilibrium is reachable, and the self-confirmation property implies that the model can achieve perfect prediction accuracy when this equilibrium is being played. So taken together, they seem to imply that the model theta would predict equally as well as any arbitrary competing model, so it would persist. But this intuition leaves out one important challenge, which is that while p-absorbingness implies that the equilibrium is reachable if the agent is a theta modeler who keeps using theta, we still need to show that this continues to hold when the agent is a switcher, when the agent is a switcher and has an additional competing model. So in fact, in the process of converging to the self-confirming equilibrium, the interaction between the model choice and the within model beliefs can sometimes lead to traps that prevent the equilibrium from being played in the first place. So for example, when there is a second model, in order for not switch to that second model, the outcome realization would inevitably lead the agent to play an absorbing action that is not self-confirming under model theta. And once the agent starts playing this absorbing action, there is no chance for the model to persist. The key lemma in this proof shows that if the agent starts out with a sufficiently concentrated prior around the self-confirming equilibrium, then the probability of leaving the self-confirming equilibrium and getting trapped is strictly less than 1. Okay, so let's summarize our findings so far. Interestingly, both global and local robustness require high asymptotic accuracy, as they both require a p-absorbing self-confirming equilibrium. The next theorem I'm going to show you characterizes the priors that allow these models to be robust. Now, we know from the previous slide that if there are traps, then the prior has to be really concentrated around the self-confirming equilibrium. However, from now on, I'm going to focus on models with no traps. Okay, so I don't have time to go through the no trap conditions today, but just to assure you that there is nothing fishy here, the no traps conditions are mild and they are stated in terms of the primitives. So for example, a no trap condition is that all p-absorbing self-confirming equilibria are quasi-strict. Okay, so given this, the remaining question is, if there are no traps, do we still need the prior to be concentrated? The answer is yes and no. It turns out that global robustness requires the prior to be tight, but local robustness doesn't. So conceptually, this tells us that limiting the step size of switching does not expand the set of qualified models, as they are still characterized by high asymptotic accuracy, but it expands the set of priors that support robustness. To state this result, let me first define a notation, C of theta. So C of theta collects the set of parameters within model theta that are associated with any p-absorbing self-confirming equilibrium. So in the artist model, this C of theta is just the demand hat. But in general, when there are multiple self-confirming equilibria, this set, C of theta, may contain more than one element. Theorem 2 says that when model theta has no traps, it is globally robust at this given prior pi0 theta, if and only if the prior assigns high enough probability to the relevant parameters in C of theta. So in particular, the assigned probability multiplied by the switching threshold alpha must exceed 1. So in other words, the prior tightness multiplied by the switching stickiness must be larger than 1. This is, let me just point out that this is a sharp characterization because it's an if and only if characterization, and it is closed form. But what it means is that when switching is not sticky, meaning that alpha is really close to 1, it's relatively easy to switch, then the prior has to be really concentrated to an equilibrium, to the C of theta. But when switching is highly sticky, meaning that we have a large alpha, then the requirement has less bite, and our model is globally robust under more priors. Now, furthermore, from this assumption, from this condition, we learned that a model is globally robust at all full support priors, if and only if the C of theta includes every parameter under model theta. So this is because when this condition holds, then the prior tightness would always be 1, and this condition would always hold. In contrast, local robustness has no prior tightness requirement. In particular, a model is locally robust at all full support priors, if and only if C of theta is not empty, meaning there exists at least one p-absorbing self-confirming equilibrium, which is the same condition that we see in theorem 1. Now, let me use just a couple minutes to explain why global robustness requires prior tightness. So the intuition is that the base factor acts like an Occam's razor. The key step to show this result is to construct a so-called simple and accurate competing model. So this competing model, theta prime, its predictions would consist of the data generating processes associated with the parameters in C of theta, this red dot here, and the true data generating process. And we're going to assume that we're going to let the associated prior to assign close to 1 probability to the parameters in C of theta. So what it means is that we are preserving the most essential data generating processes in model theta and adding the correct data generating process. We assign the true data generating process just a tiny probability so that, by and large, this competing model could be, it's almost a subset of model theta. It turns out that if model theta is the eventual model choice, then the base factor is approximately given by 1 over the prior probability of C of theta assigned by the prior under model theta. So let me explain why this is true. So if the agent eventually adopts model theta, then since the competing model contains the true DGP and it is correctly specified, it means that the agent must play a self-conforming equilibrium in the limit. And therefore, the best fitting parameter must be an element of C of theta. And so given this, the data fit of model theta would be approximately a fraction of the model fit of model theta prime. And this fraction is exactly given by the prior probability assigned to C of theta. And so given this, theta can persist even only if the base factor is lower than the switching threshold alpha, which then reduces to this condition. Now, the actual proof of this is more complicated than this, because there are other complications, such as what if we have multiple p-absorbing self-conforming equilibria? Then the agent eventually converges to one of those equilibria. So it's not obvious whether the relevant prior probability should be the sum of all prior probabilities or the prior probability of one single element in C of theta. So the rest of my proof deals with those complications. Just finally, I want to close this proof intuition with an interesting observation. Now, this phrase here, simple and accurate, is actually quite misleading because the competing model doesn't have a tight prior over the true data generating process. So instead, it has a tight prior over the set of p-absorbing self-conforming equilibria. So what it means is that the competing model outperforms the initial model, not because it is simple and accurate, but more because it is sufficiently extreme and sufficiently misleading. Great. And I want to, so this is probably the last result I want to convey today. I think these results draw some interesting comparison between misspecified and correctly specified models in terms of their persistence properties. So on one hand, correctly specified models are always locally robust and always globally robust for at least one prior, because they always have the highest asymptotic accuracy. However, some misspecified models may have even better robustness properties, especially if they have more self-conforming equilibria or they have a smaller parameter set, because these properties make it easier to satisfy the prior tightness requirement. In a paper, I applied this insight to a media consumption problem and showed that a simplistic binary political view can outperform the more complex correct view. What happens is that a binary political view has a binary parameter set and gives rise to exactly two self-conforming equilibria. In the first equilibrium, the agent subscribes to left media and believes that the state of the world is left. In the second equilibrium, the agent subscribes to the right media and believes that the state of the world is right. So such a model is globally robust at all priors. And therefore, from this example, we learned that we can have echo chamber and political polarization in a robust and persistent way. The other implication I want to point out here is that low switching stickiness could be a double-edged sword. Let's consider, for example, a thought experiment where we make the agent more willing to switch by decreasing the switching threshold to be close to 1. Then on one hand, this makes it harder for misspecified models to persist because it's harder to satisfy the prior tightness requirements. And this is good. However, it also makes it harder for correctly specified models to persist, which is not good. So intuitively, if the agent is more open-minded to innovations, then he might abandon his initial correct model too fast after observing some rare events. And then he would get stuck with a misspecified alternative. Okay, now let's come back to this matrix. I have characterized local and global robustness by asymptotic accuracy and prior tightness. And just in the interest of time, let me just mention the other notion, constrained local robustness. It turns out that the constrained local robustness needs neither one of them. So it only requires a local notion of asymptotic accuracy that relates to the Burke-Nash equilibrium rather than the self-confirming equilibrium, such that at this equilibrium, the model is a local best fit relative to nearby models in the same parametric family. So the quick takeaway from this is that more misspecified models can persist if the agent is constrained in her direction of exploring competing models. In other words, it takes a model to beat a model. Okay, in the paper, I also consider a couple of extensions of my learning framework, and I am happy to talk about them after. But right now, let me just conclude. This paper builds on the literature on learning with one misspecified model. And a large strand of this literature focuses on specific biases. There are papers focused on equilibrium concepts that can be used to characterize asymptotic behavior. And the recent strand of the literature characterizes asymptotic behavior and beliefs in general environments. And I think my contribution to this literature is mainly like threefold. So first of all, by characterizing robust models, I provide a learning foundation for certain types of misspecified models. And second, my results show that self-confirming equilibrium and Burke-Nash equilibrium are related to different robustness notions and has different perspectives when it comes to competing models. And the third contribution is more technical. So I incorporate a model switching process to an active learning process. And this is not trivial because not only do we have endogenous actions and beliefs, but also endogenous model choices. And all of the three can interact with each other. This paper is also related to a literature that compares different models. And within this literature, this paper falls into the category of comparing models based on their statistical fit. But other papers in the literature compare models by their objective payoffs or subjective anticipatory utility or payoffs. Okay, so this paper develops a novel learning framework that incorporates model switching into active learning. I use this framework to define persistence and characterize notions of robustness. I think there are many ways to utilize this characterization. It can be used to provide learning foundation for misspecification. It can also provide off-the-shelf tools to determine which biases are more relevant than others in different environments. And hopefully this can shed light on the direction of new empirical research and policy making. So for example, if we want to mitigate the consequence of misspecification, it would be good to know which biases to target. If underconfidence is less persistent, then it requires less intervention, for example. And I think this learning framework can, within this framework, there are many other interesting theoretical questions to explore in the future. So that is my paper. Thank you for your attention, and I am happy to take any questions.
Okay, well, thank you very much. That was spot on with respect to the time, especially. Drew Botton, do you want to?
Yeah, I have one more question. Cuimin, you pointed out that this simple binary view can be stable. Mm-hmm. Okay, but the slide said it outperforms the correct view. What do you mean by that? Is the correct view not stable? I would have thought it was. So what's the performance? So I don't quite understand that bullet yet.
Great. So let me clarify this. In that application, so I first consider what happens if the simplistic political view is the initial model. And I also consider what happens if it is the competing model. So what I mean by outperform is that when it is the competing model, it can, with some probability, replace the correct view. And then, because it's globally robust at all priors, with positive probability, the agent can get stuck with it.
But is the correct view also globally robust at all probabilities?
The correct view is globally robust for
exactly.
entrenched priors. For entrenched priors.
Only entrenched priors.
For all priors. Yes, because it's more complex.
Why is it more complex?
That is because I consider a more complex correct misspecified model. So there, of course, could be
hold on. The correct view could be a point model on the exact true model. I don't see how that's not robust.
Great. So a lot of models can be correctly specified. One of them is true.
So the correct view, you mean can outperform a model
correct view.
which happens to contain the correct view if it contains
Yes.
enough other incorrect views.
Exactly.
Okay,
Thank you.
well that would be less surprising, but more correct. So thanks.
Thanks. But just to maybe offer a different explanation. So the correct view in there is the correct view that I take in this example is that the world could be left, it could be median, it could be right. So in some sense that is correct, but I also take the true state of the world to be the middle state. So that's why the correct view in some sense is correct in a changing world.
That's
but
a
it's not
correct view. I mean, the true state is middle. The correct view is a point mass on middle. I think you're still being a little misleading in calling this thing the correct view.
Yes, I take your point. Yes, thanks.
Drew, did you have any other comments or questions, or should I pass it on to Bhutan?
I'm happy to pass it on to Bhutan.
Okay, Bhutan. Do you have any comments, questions?
I have a couple of questions, but let's see if others have maybe. I really enjoyed it, so.
No, just go ahead. We normally do it this way. We'll open up the floor later on.
Yeah, so I was wondering a little bit about these statistical fit. It's kind of perhaps a question on the more than your paper, the statistical fit criterion. So that it's asking, I feel like it's asking a lot of your agents. Basically, you've made some conclusions based on your model, and then you're asking them to kind of step back, forget all the conclusions they've made, and evaluate the data again using another model and compare the fit.
Yes.
It seems to me that that's very difficult to do. Basically, I make some conclusions about the world, what, I don't know, Trump or whoever is like. I make those conclusions, and then you're telling me, okay, just forget all that, and let's see whether something else explains the data. But I can't forget what the conclusions I've made. So maybe this is pointing too far, but I was wondering.
Okay, I think it would be plausible in some settings where we have not only one agent, but an institution, and different parts of the institution could be in charge of different things. So in the central bank, we can have the chairman in charge of which actions should I choose based on the estimates of the economist. And the economists can have two groups, one in charge of estimating the models and the other in charge of comparing different models. Now, for the individual case, I'm not sure so sure what you have in mind. Do you have in mind what would be a more realistic way to capture this?
No, I mean, it's unfair in the sense that I don't have a more realistic way. It's just well, or I don't have a precise statement of it, but that somehow you don't forget the conclusions you've already made and try to compare the models somehow colored by the conclusions you've already made. I don't know how to formalize that though.
Okay, I guess, so think of as an economist what we usually do in daily life. So we take a model, we estimate our model, we make some policy predictions, but it could happen that in one of the experiments, the data showed the data that we obtain would be much better explained by an alternative model that we have in mind. And at this point, we switch to the competing model, but we also preserve all of the data that we have collected before and use that to inform our the estimation of our new model. Yeah, I hope that would be something.
Yeah, that makes sense. So partly I started thinking about this, that you gave scientific revolutions as the example, and I just see how difficult it is for scientists to give up their models. Like, it takes a couple of 100 years for them to give up their previous
Yes, that's exactly my motivation for assuming that there is switching stickiness. The alpha could be really, really large.
Bhutan, you said you had two questions.
The other one is more specific, where I mean that if nobody else has a question, then I was confused, or I lost you a little bit on slide 27 when you were here. So the this last line, if empty eventually equals theta, so why that's true, and then how it's related to the line below it.
Great. So this is true because if the model trace eventually equals model theta, that means that since model theta prime is correctly specified, then the agent must, under model theta, play a self-conforming equilibrium. This means that her belief eventually converges to some element in C of theta. And so when we compare the model fit between theta and theta prime, which is the prediction power of model theta would be a fraction of the prediction power of model theta prime. And so that ratio.
Let me slow you down there. You said that the belief has to be a single element of C theta, whereas I would have thought it had to be in the convex hull of C of theta. That you haven't yet said beliefs converge to a point mass on a particular model, particular parameter set.
Thank you for thank you for pointing that out. So what I said is a little imprecise, but it's also true. So why the agent's belief converges to one element in C of theta? Because I made a set of no trap conditions earlier, and one of them happens to be an identifiability condition, so that different parameters correspond to different data generating processes and different distributions. That's why. But just here, I am just describing.
So I missed that. So it's different parameters have different implications for every single action.
Yes, exactly.
Thank you.
Yes, exactly. But given that, then the prediction power of between model theta and model theta prime would be a fraction. Now, this would be most simple to understand if C of theta is a singleton. So let's just assume it is a singleton. Then the fraction, the ratio of their prediction power would be the ratio of the prior probabilities their priors assigned to C of theta, right? And so this would be pi 0 theta prime of C of theta over pi 0 theta of C of theta. And since the prior for theta prime is close to 1, the probability assigned to C of theta is close to 1, this would be like approximately given by 1 over pi 0 theta of C of theta. And so if the relevant cutoff for a switching decision is the switching threshold alpha. So if we compare this ratio here to alpha, the models persist if this ratio is lower than alpha. And so if we rearrange that condition, that would mean the prior probability multiplied by alpha would be should be larger than 1. And conversely, if the ratio is larger than alpha, then we must have the agent switching to the competing model. That's why it's sufficient and also necessary.
Okay, I see. And then you said that this is alternative model is extreme and misleading.
I say it's extreme and misleading because notice the way I construct it. It is preserving the most extreme, is preserving the most misleading part of model theta, right? Mm-hmm. It's the parameters that are associated with those self-confirming equilibria, the misleading part. Now, the extreme part comes from the fact that I assign very high probability to those misleading parameters. Does that make sense? And so this competing model wins not because it's simple and accurate, but because it's extreme and misleading.
Okay.
In the usual sense, when we think of the Occam's razor, we think of it as selecting good models with simple and accurate. But here, when in my setting, it turns out it was like extreme and misleading models.
Thanks.
Thanks.
Okay, it's 5:15 here in the UK, so we're gonna stop the recording and end the formal part of the presentation. I just wanted to